Motion of a falling object. My name is Jake Nelson. For our table of contents, we have Newton's second law and the momentum principle. We're going to establish the initial conditions. We're going to go over the experimental procedure and how the data was collected. We're going to go over computational steps, and results and comparisons, and conclusions and further questions. And so first of all, the purpose of this experience was to observe the motion of an object and generate 3 different position versus time graphs. One graph is an experimental model through tracker, and 2 computational models that were developed with and without the drag force. The goal was to model the effects of gravity and drag on a falling object's motion. So some key concepts are Newton's second law, which explains how forces acting on a system can change its momentum over time, and it's also known as the momentum principle. And then the drag force is a frictional force which is proportional to an object's velocity squared. And the weight force, or the force of gravity, is a force that acts vertically downwards on an object. For our procedure, the first thing we did was record a video of an object being thrown. Then we analyzed the video using tracker and extrapolated the data. Then we manipulated the starter glow script code to create 2 computational models. One where F net was just the force of gravity, and one where F net was the force of gravity and the force of drag. Then we created a position versus time graph to compare the models. Then we drew conclusions. For our initial conditions and tracker analysis, our initial velocity was 2.27, 1.31, 0 meters per second, and the initial position was 0, 0, 0. Motion is in the positive x and positive y direction at first, but then our system is the paper ball, and the surroundings are of earth and air. For our computational model for drag and gravity forces, you can see that F net is equal to the force of gravity plus the force of drag, because this includes the drag force. And for this one's only gravity, so F net is only equal to the force of gravity. And then this is our comparison graph that we got from both the real-life video and the computational models. So you can see at first, all the data is similar, though as time goes on, the force of gravity and drag change the position coordinates. And you can see that the gravity-only model has higher y positions as it continues. And then the gravity model and experimental data match much better than the one with both drag and gravity. And so for conclusions and further questions, for which model predicts terminal velocity, and what does terminal velocity mean for the net force? Both the experimental and gravity plus drag predict terminal velocity, and terminal velocity means that the net force is 0, because it's when the drag force equals the force of gravity, and so the resultant net force is 0, and there's no acceleration. And then what if the object was thrown straight upward with the same initial speed? If that was the case, then the terminal velocity would still be the same value, but since it's based solely off the object's properties and mass, however, the time to reach the terminal velocity would be different, because in this scenario, it's thrown straight upwards and has all of its velocity in the y direction.